Hello everyone. My name is Enes Goktas, and I'm going to present our work in which we looked at a new security feature in LLVM Clang, which is called SafeStack. It's quite recently added to the compiler. So let me give an outline of the presentation first. So I will first explain what SafeStack is. We will look at what it is good for, look at it a little bit at its internals, and then we will look at its weaknesses. So we will look at neglected pointers, which are implementation issues. Then we will look at two more fundamental problems like thread spraying and allocation oracles, and then we will conclude the talk. So SafeStack, what is it? As I said, it's a new security feature in the compiler, in the LLVM toolchain, and it's essentially against to prevent control flow hijacks on the stack. And originally, this has been proposed by researchers Kuznetsov and others in the code pointer integrity paper. In this paper, they tried to hide and protect all the code pointers because attackers exploit the code pointers. They try to overwrite them and then get control of the program to do malicious stuff. For example, execute a rob chain and in the end, take control or compromise the machine or the computer. So, and it has also been proposed for integrating it into GCC. I think some FreeBSD developers are thinking of providing the SafeStack feature out of the box. So this means that if you install a FreeBSD operating system, probably you will have the SafeStack feature on in its default configuration. So it's actually, quite a thing that people look at it right now, and we also wanted to look at it, but from its security perspective, how safe is the SafeStack? So what is SafeStack doing? So let's say let me show this with an example. So here we have a node in a program where SafeStack is not applied. The stack contains the program execution context of the process, and it has code pointers, the return addresses, it has local variables pushed by the functions. And what SafeStack does is when you apply SafeStack, it separates values on the stack. So it adds an additional stack, an alternative stack, which contains address taken, which they define as a dangerous data that can potentially cause problems like overwriting the code pointers on the stack, like the return address. I will show this with an example. So what is it good against? So let's say we have a memory corruption in the program, and buffer A can be overflown with data. So what the attacker can do is if it overflows the data in buffer A, it can overwrite the return address. This is very valuable for an attacker because here it can initiate the control flow hijack of the program. But when you apply SafeStack, the vulnerability will happen on the unsafe stack, and the attacker cannot overwrite the sensitive information, the sensitive data, the return address, code pointer on the stack. So it's good against, so it protects the return addresses. So it is good against stack buffer overflows that try to overwrite the return address on the stack. But it is also good against some other problem. So let's say we have a variable in the heap that has a pointer that is a pointer to the buffer A on the stack. So if the attacker has some information disclosure capability, it will be able to leak the location of the stack and continue its exploitation. So the thing is, the stack should actually be hidden from the attacker. And if the attacker can find the stack, it also needs arbitrary, some write capabilities to then overwrite the values on the stack. So information disclosures, that's the thing. So the thing is, buffer A will then be moved to the unsafe stack when you apply SafeStack. So the buffer A pointer will not be pointing to the stack that contains the return addresses, but it will point to the unsafe stack. So it also stops actually the stack location disclosure. So it prevents also leaking the stack location. So how does it look in the process memory? When you apply SafeStack, it separates the values in the unsafe stack and puts the unsafe stack in the mmap area. So nothing interesting. The interesting part is, as I mentioned already, if there's a pointer to the stack, this pointer will be pointing to the unsafe stack. So the safe stack will be protected from having pointers to it. So pointers to safe stack may not appear in reachable memory to keep the safe stack hidden. So we want to hide the safe stack from the attacker. And with reachable memory, I mean, so if the attacker has information disclosure capabilities and it starts leaking data, it can leak the data regions, and it can follow pointers to other regions and try to leak as many as possible in the memory space. That's the reachable memory, and preferably there should be no pointer to the safe stack. So let's also look a little bit at the internals. Here's an example, a main function with a buffer. This buffer is being provided to string copy. And this is not really a safe program. An attacker could provide any length in the argument. Okay, so that 0 should be a 1. So if the attacker provides a very long argument, it will overflow the return address on the stack. And so that's the problem here. How does it look in the assembly code? The second block shows some assembly code where SafeStack is not applied. This piece of assembly allocates some space on the normal stack for the buffer. So the buffer is located on the normal stack. And when it calls string copy, it gives an address. It provides the address of buffer to string copy, and it actually operates on the stack. And in the SafeStack example, the buffer is located on the unsafe stack. The unsafe stack is maintained through a pointer in the thread local storage. It retrieves this through the fs register. Fs register is a special register that contains the base of the thread control block, and so it takes an offset from this fs register and gets the a pointer from the thread local storage and then stores the buffer on this unsafe stack. So it doesn't use the RSP pointer, but it uses the FS register and takes an offset to get the unsafe stack pointer. So instead of using the RSP pointer and getting an address to the stack, it gets an address to the unsafe stack. So in the third block, in the safe stack example, it retrieves the address from by reading the value in R15. And in the normal example, it uses RSP. Okay. So SafeStack can be enabled by setting the SafeStack sanitize flag. And essentially, moves the address taken objects to the alternative stack, which prevents, in the end, leaking the stack location, the location of SafeStack. And it relies on ASLR. But our question is, how safe is the SafeStack actually? And for this, we look at these two things. So can we still leak the location of the SafeStack? And because it relies on ASLR, can we weaken this reliance? So we will look at three problems. One is that there are still pointers actually in the program. We will go over them. And then two more fundamental problems like thread spraying and allocation oracles. Okay, let's start with the neglected pointers. But before we start, we are assuming that the program has a memory corruption and that this memory corruption enables an attacker to have an arbitrary read-write primitive, with which the attacker can leak the heap and module data. So it can read out the data, but it doesn't know where this stack is. And the goal is to locate the safe stack. So SafeStack ensures there are no pointers to the stack. So what we did, we analyzed some programs with Python script and used GDB. We walked the whole memory space and then just looked for pointers that would point to the SafeStack region. So we collected the stack locations and then just went over the memory and then collected addresses that would point to the collected stack regions. And then we manually verified the pointers. So we found pointers and we categorized them in three groups. Like we found pointers in the heap, we found pointers in libraries, and something very interesting is are the thread IDs. We will look at that. So what we found in a heap, we found some thread management related structure, which is called dynamic thread vector. This contains pointers to TLS blocks, so the thread local storage blocks, and a thread local storage corresponds to a module library, this module has its own thread-specific values, which it stores in its own thread local storage block. Libraries and modules that are loaded with the program at the load time of the program create static TLS blocks, and libraries that are loaded later during runtime, they create dynamic TLS blocks. Okay. So in this dynamic thread vector, there are pointers that point to the stack, but how? So the thread control block is located on the stack, and the static TLS, thread local storage blocks, are adjacent to this TCB, to this thread control block. And DTV, the dynamic thread vector, points to the static TLS block. So in the end, it also points to the stack. So you have pointers in the heap that point to the stack. If you would like to know more about the structure, so here it's all about the pointers, but if you like to know more about the pointers, you can follow this link to read more about thread management and TLS blocks and TCB blocks. So there are also pointers in the libraries. Two very interesting ones that could give you all stack locations are the stack used and the stack user variables in the pthread library. So the pthread library uses these two variables to do its thread management. Stack used, so these two variables are linked lists that point to the TCB, which are for secondary stacks. So for secondary threads, so what are secondary threads? So you have a main thread that is created by the kernel. So when the program starts, you have one stack that is created by the kernel. That's the main stack. And the threads that are created afterwards during runtime, those are the secondary threads. And stack used points to secondary threads, stacks, and stack user points to the main thread. And actually, they point to the TCB. And as I said, the TCB is on the stack. But for the main thread, the TCB is not on the stack, but in the heap. So that's also interesting. But if you have the TCB, then you can get the stack because the TCB, the thread control block, has itself also a pointer to the stack, like where the stack starts and how large the stack is. Okay, so that's stack used and stack user. There are also other pointers. So for example, in libc, there is the program invocation name and a program invocation short name. These just point to the name of the program, but these are located on the main stack. So on the main stack, you have the stack itself, but also just before the stack, you have its environment variables and argument list. And there, these two variables point to. libgcc, as the variable names say, have these two pointers point to the argument list, also on the main stack. The LD library, the loader, also has some pointers. As the names say, environment point to the environment list, dlrv points to the argument list, and libc stack end points to the start location of the main stack, so where the stack starts growing. And RTLD global RO structure is a very large structure, but it also has some pointers to environment variables. So there are pointers. Yeah, that can be fixed. But another interesting one is the alloc end. So alloc end is used to in the memory management. So when an application calls malloc, it uses alloc end to see where the last allocation was, and then it allocates more at that location. But if the application overloads malloc like Chrome and Firefox does, this alloc end becomes like a stale pointer. And this brings us back to the TCB and the dynamic thread vector that is allocated for the main thread. These two are allocated in the heap. So these are the first two thread structures for the main thread. These are in the heap. And alloc end points to the region that contains these two structures, so the dynamic thread vector and the TCB block of the main thread. Yeah, so it's a stale pointer that points still to the region that has some interesting structures. So an attacker could get this pointer. Another interesting one is the thread IDs. pthread API, so the API for creating threads and managing threads use a thread ID, the pthread T type, but this type is not just some number that indicates the nth number of thread, but it's the address of the thread's TCB block. But TCB is on the stack, so so if the application does some thread management and puts pointers, stores the thread IDs in its data region or the heap, it is storing pointers to the stack actually. And this was very interesting. Also, libraries can, here an example like libxml2. The library stores a pointer to the main thread's TCP. Actually, that's not the purpose, but that's what happens. Okay, so let's assume these implementation issues are fixed and there are no pointers pointing to the stack. Then what an attacker could do is try to randomly hit the safe stack. But the address space is so large that its entropy is very high. So the chance that you hit the stack is quite low. So what could he do to increase his chance to hit the safe stack? Well, reduce the entropy through thread spraying. But let's first go over what is entropy actually. So entropy is a degree of randomness of something in the memory that is given in bits. So let's start with a simple example in which where we have a 3-bit address space, and then we will look at the 64-bit address space. So this 3-bit address space has 8 blocks contains 8 blocks of 1 byte each, and in the figure on the right side of the slide, we are trying to hide 2 bytes, this memory region. Since it is occupying, consuming 1 bit of the 3-bit address space, we say this memory region has an entropy of 2 bits, so it's consuming 1 bit. From this entropy in bits, you can understand that the hit chance is 1 divided by 2 to the power of 2, which is the entropy, which is 25%. So if you try to randomly hit the safe stack or this memory region, then your chance of hitting it is 25%. And if you have a probe capability and you're trying to probe for it, you would need 4 probes in the worst case. Okay, so if the memory region would be 4 bytes, you would occupy half of the address space, or this 3-bit address space. It would occupy 2 bits of the address space, and entropy would be 1 bit, which means that the hit chance is either 50% or the worst case probing number of probes is 2. Okay, so let's now look at the 64-bit address space. If we try to hide 1 byte, the entropy of this 1 byte is just 64 bits. With Linux, in the user space, it uses 47 bits for the addresses, so entropy reduces a bit. So it's 47 bits. If you try to hide that 1 byte in the Linux address space. But you cannot just allocate 1 byte in the address space, because memory allocation happens on a page granularity, which is 4096 bytes. So you will be allocating 2 to the power 12 bytes, so it will consume 12 bits of the address space. So first entropy was 47 bits for 1 byte. For 4096 bytes, this entropy reduces to 35 bits. Okay, so in Linux, the default stack size is 8 megabyte. This consumes 2 to the power 23 bytes of memory, and which means the entropy for one safe stack is 24 bits in the 64-bit address space. So I explained this to get to the thread spraying concept, because thread spraying is about legitimately trying to spawn as many threads as possible in the program and to reduce the entropy. So we want to have the entropy as low as possible. What can we do? So we can spawn another thread. If we double the size of the stacks in the memory, the entropy reduces by 1 bit. If we double the size again, it reduces the entropy of the stacks by 1 bit again. So if you can spawn like 128,000 threads, the entropy So finding a stack becomes, like the entropy for the stacks becomes 7 bits, which means that you would need, so the worst case, the number of probes would be 128 probes. The interesting thing is that in Linux, mmap has an entropy of 40 bits, which causes to drop the entropy for the 128,000 threads, the stacks, to become, oops, not there, 0 bits. So the idea is to spawn lots of threads and just to reduce the entropy and increase the hit chance. Because, yeah, we don't have pointers and we want to find the safe stack. So we inspected several applications. So I will go over Firefox and MySQL, how we could spawn many threads and spawn stacks. So in Firefox, when you start a dedicated web worker in JavaScript, it creates a new thread. But the number of threads, the number of web workers is limited. You can just create 20 web workers per domain name. And the web worker thread stack size is 2 megabytes, and its entropy of this stack is 19 bits. So how did I compute this? So Linux, as I mentioned before, has an entropy of 40 bits, like because it's using mmap for the stack. It has an entropy of 40 bits. 2 megabytes occupies 21 bits in address space. So the stack has 90 bits of entropy. So if you are trying to hit this stack, you would need about 500,000 probes. Quite a lot. If you spawn 20 threads, this number of probes reduced to 30,000, and entropy is 15 bits. But we can do better. We can load more. We can cause the page to have more. Well, we can through iframes we can load pages from other domains. And there's no limit on the number of iframes in the page. So with this, you can have an unlimited number of web workers in the page. So for example, if you spawn 16,000 web workers, you would drop the entropy to 5 bits, which is quite low. And the number of probes will be 32 probes. So in the worst case, you would need 32 probes to hit this, to hit a stack. In MySQL, a new thread is being started with every network connection. And the number of connections is 151. That's a default, in the default configuration. The thread stack size is 256 kilobyte, which has an entropy of 22 bits. And if you exhaust the connections, so if you start 151 connections to MySQL, you will be having 151 more stacks in the address space, and its entropy reduced to 15 bits. But as we assumed, an attacker has the arbitrary read-write capability. And in MySQL, the number of connections is regulated by a variable max connection. So if the attacker changes this variable, it can create more connections to the server, to MySQL, and start more threads. But it can also regulate the, it can also modify the stack size, because this is also just in the data region of the MySQL binary. So if an attacker sets the max connections to 4,096 connections and the stack size to 256 megabyte and exhaust the connections, it would reduce the entropy of the stack to 0 bits. So Linux uses the 7F region in the address space. So it would exhaust the 7F memory region, and by exhausting this region, this address shown on the slide 7F000 has a very high chance of having of locating a safe stack. So by spraying lots of threads and spawning stacks, ASLR can be weakened, and the chance to hit the safe stack will be increased. But spraying might not always be possible. For example, in Firefox, we were just lucky that by loading other pages, loading other domains, we would be able to start more threads. And in MySQL, we could play with some variables in the data section. But for example, in Nginx, you might not be able to spawn more threads if it's not configured as being multi-threaded, for example. For this, there's a new approach. You can use allocation oracles. Quite interesting. Let's see what it is. So let's look at the memory space again. So we want to find the safe stack, but there are no pointers to it, as we assumed, and we cannot spawn threads. So how can we find the safe stack? So interesting to note is there are holes in a memory space. If we know the size from the heap to the safe stack, we can infer the location of the safe stack, because the attacker in the threat model knows the location of data and heap. It's all disclosed. So the location of the heap is known and where it ends. If we can infer the size, we can, the size between the heap and the safe stack, we can get to the safe stack by just adding the size to the heap location where it ends. In this memory model for the process, these three holes have a minimum and a maximum size. So what the idea is that we will try to allocate large chunks of memory by doing this repeatedly, we will try to infer the size of the hole. So we will allocate some memory, and if it succeeds, we know the hole is probably larger. We will try again. We will try a much larger size. If it fails, we know this hole is smaller. And we will repeat this until we find the right size of the hole. And this is done with a binary search, so it's quite fast. So one primitive, so there are two primitives. We define two primitives. One primitive of allocation oracles is the ephemeral allocation primitive, where the allocated memory is short-lived. So it gets allocated, but shortly later it gets deallocated. And it looks as follows. So you control the size of, for example, malloc function. It allocates some memory, but later it frees this location, this memory, and then it replies the result to the client. So the strategy is the client sends a request to the server allocates some memory, and then the server responds with the result to the client. And the client can infer what happened at the server. So let's say we inferred the size of memory region of the whole A with the short-lived primitive, but we want to know the size between the heap and the safe stack. So we have to continue allocating and finding the size of this region. But because the allocated memory, if we do it with the short-lived technique, the memory gets deallocated. So we need something to keep that region allocated because we want to continue. We want to build on top of it. We want to have that. We want to keep it there, and then we want to do the. We want to probe again for the for a whole size, and then we want this to end up in hole B. So what can we do? Then we can use the second primitive, the persistent allocation primitive. It's quite straightforward. In this primitive, the allocation, we prevent the deallocation of the memory. Usually we can transform the short-lived primitive into a long-lived primitive by, for example, keeping the connection open or just not completing the request reply communication. So we can keep the memory allocated for hole A, and then we can use the short-lived primitive to get the size between heap and the safe stack. And once we have that, we can compute the address of the safe stack, and then we know where the safe stack is. So how can we do this, and what do we need? We need a way to allocate large regions. We need to find a way in the program, and also we need a way to infer like what the server did. So in Nginx, you can what we found is that you can change the this variable in the memory, the pool size, and when a new connection happens, it will use this pool size to allocate the memory. And we found this by using a taint propagation framework in which we taint the whole memory when the server is idle, and then we send a connection to the server, and then we follow the taint propagation, and as a taint sink, we set the arguments of memory allocation functions. And in this way, we found the pool size. And a way to detect whether the allocation at the server failed or not, there are different kind of options. So one is the server just replies with a status. It says, it gives you the page that you requested, or it just says something wrong happened. Or it just, so it can, so the other option is that the server crashes, so it just doesn't reply anymore, so the connection closes. Or it gives you, when it succeeds, it gives you an OK status and gives you the page. Or a timing side channel can happen. So an example I will show you in which server we use such as a side channel. So in a side channel, you measure the time, and then the time for the response, and then if the server replies quick, it means probably everything was fine. Well, of course, it depends on the server, but yeah, you can infer like on the response whether it succeeded or not. Nginx, for example, when the allocation fails, it closes the connection. But LightTBD, it crashes. So the reason that LightTBD crashes is that when it allocates the large memory region, it tries to initialize this region. Imagine, so it allocates a large memory region, and when it allocates, it's not a problem. But when it starts initializing the memory, it starts using physical memory. And if there's not enough physical memory, it will run out of memory and then it will crash. But the nice thing is, if the allocation fails, the response will take long, and if it succeeds, it will be much faster. And then light-TPD restarts when it crashes. So the assumption with allocation oracles is that a memory overcommit should be enabled. But in some servers, this feature is enabled because it also hosts like big data software like Redis, Hadoop, or virtualization. In such cases, memory overcommit might be needed. And interesting to note is that, for example, in Android, we learned recently that memory overcommit is enabled by default. And even if it is disabled, an attacker can still try, might be able to do allocation, might be able to execute allocation or oracle primitives if he can control the flags of memory when memory is being allocated. For example, if it can set the map no reserve flag in mmap, it doesn't look at the memory overcommit flag. It just allocates the memory without reserving any physical memory for it. To conclude my talk, implementing safe stacks without pointers to it might not be trivial, as we have seen. There are quite some pointers to it. Some effort is still needed to fix all of these pointers. ASLR is maybe not a good thing to rely on, because there are different ways you can weaken it, like thread sparing and allocation oracles. And we think that the proper isolation, like software fault isolation, or where you put binaries on memory access, might be a good way to protect SafeStack and mitigate these attacks. If you are interested in these talks, in these topics, then you might also want to read the papers that have more information about these techniques. Thank you for listening, and if you have questions, I would like to answer them.